So starting our last video notes for the entire year. It's crazy to think that we are at this point here, but I just wanted to start this video off by thanking you all for making my first year at Pikeville High School so amazing. It has been challenging at times. We know how that first unit went and the start of the year, but thank you all for your perseverance, your patience, and really just your hard work. How you all work matters a lot. It's going to pay dividends on the test coming up, but most importantly, it's going to pay dividends in your life. The habits that I hope I've helped you build of hard work and persevering when things are hard and having to push and challenge yourself and grow as a learner yourself, I hope those pay off here. So enough of my yapping, let's go ahead and get started. What we're working with today, really, it says equivalent representation of trig functions. We're really working with trig identities. Like, we're working with trig identities and basically different forms and different formulas that are really helpful to use with trig equations. When I think of trig, when I saw that there was for the first time, I saw that there was a trig part on our AP Pre-Calculus course. I thought first of the unit circle, and second thing I thought immediately was trig identities. Like, these are super important now, and they are super, super, super important for your classes later, especially in calculus. So let's make sure to lock in and get these. So in this section, we will explore several ways to write equivalent expressions of different trigonometric expressions. We already have several tools in our math box that we can use to write in equivalent forms. And these trig identities here, like, these are just opposite ways to write stuff. So as we know, sine is 1 over cosecant, and cosecant is 1 over sine. Like, they're the same thing, just flipped. So all of these are the same thing, just flipped, right? These are the same thing, just flipped. Tan is like the reciprocal 1 over cotangent, and cotangent is 1 over tangent. And an important one always is that tan is sine over cosine, and then because cotangent is just tangent flipped, cotangent is cosine over sine instead. And knowing these allow us to manipulate trigonometric expressions and rewrite them in equivalent forms. So we have f of x on example 1 here. It wants us to rewrite an expression involving tan x and no other trigonometric identities. No matter where your starting point is, something I think to be helpful, like when I'm trying to rewrite in different forms, even though it says to write it in terms of tangent, my first step is always going to be to try to write in terms You're always going to try to write in terms of sine and cosine first. Like, you're like, Mr. Hampton, it wants tan x. Why are you bringing in sine and cosine? Well, remember, tan is just sine over cosine, and this is going to take care of a lot of issues when we try to simplify these. Sorry, had some technical difficulties, had to restart here, but solving this, we've got f of x equals sine x. And when you break apart this right here, whenever it's secant squared, remember, I'm trying to write it in terms of cosine and sine first. Remember that if it's squared, you're going to have to square both parts that you break it into. Secant squared is the same thing as 1 squared over secant is the same thing as 1 over cosine. So 1 squared over cosine squared x. And it might feel a little bit arbitrary to write 1 squared right there. It's like, duh, it's 1 over cosine squared. Mr. Hinton, I just want you to get in the habit, because say, for example, you were writing tan squared x, you would have to square the top and bottom. So just wanted to get you in the habit of doing that. So once you get enough practice and you want to leave that out, that's totally okay. But for now, let's do that. So, and on bottom, we're going to have cosecant x, and cosecant, once again, it's just sine. So we got 1 over sine x on bottom. Now, let's go ahead, let's multiply the sine x on top here, then we can keep change flip. So I'm going to have sine x over cosine squared x all over 1 over sine x. And if I keep change flip that, I've got sine x over cosine squared x times sine x over 1, which is sine squared x over cosine squared x. Sine over cosine is tan, and there's 2 of them, so it's tan squared x. Okay, so see how, even though it wants me to write in terms of tangent, it's super important to write in terms of sine and cosine first. So even here, like even for secant, I'm always going to write it into, like, there's not even a, really, like, just looking at this, there's no sine and cosine anywhere here, but starting to write it in terms of sine and cosine is helpful. So let's rewrite that. Cosecant can be written as, looking back up at our chart, cosecant is 1 over sine, so I've got 1 over sine x times tan x is sine x over cosine x. If I multiply those across, multiply these 2 fractions, I get sine x over cosine x. Oh, let's write the sine first, sorry. So, like these multiply together to give me sine x cosine x. These cancel out, and that gives me 1 over cosine x. And it wants it in terms of secant, which is convenient because secant right here is just 1 over cosine x, so secant x. So g of x, this is just a fancy way of writing secant of x. And honestly, this is, once you get the hang of this, I think this is some of the most interesting thing to do at all. I think this is some of the most interesting parts to do at all. So additionally, we can discover several interesting properties that arise from our understanding of the unit circle and trigonometric functions. Let's relook at our unit circle. So remember, I've got my x and y coordinates. Cosine is x, sine is y. And really, this is the same triangle that I had you all draw before, right? Like when we started working with sine and cosine and tangent for the very first time in this class, I had you write this little triangle here, and you had all the different functions, right? Like sine of theta was y over r. Cosine of theta is x over r. And tan theta was y over x, or sine over cosine. Well, let's take this in terms of just our unit circle. Let's adapt this triangle. We're going to rewrite the same triangle, okay, with the things that we know about the unit circle. So this is the unit circle triangle. Like this is the way you can remember that. So our x value here, we know x is cosine of theta, y is sine of theta, and on my unit circle, the radius is 1. Okay, well, let's use a Pythagorean theorem to get an identity to work with. So if we know this is cosine of theta, sine of theta, that, I've got a squared plus b squared equals c squared. We'll see my a is sine. You can do sine or cosine in either order, but you'll usually see it like this. So sine squared theta plus cosine squared theta equals 1. So just from writing my parts of the unit circle here, I'm just highlighting to show you where I plugged in everything from, I get this super important identity that if I have an angle theta and I do sine squared of that angle theta and add it to the square of cosine of that, is going to add to 1. So this identity is pretty remarkable and it's really useful. So like this is your baby. This is the Pythagorean identity because we use the Pythagorean theorem to figure it out. And you'll see it here. I'll show you the math that they're doing here. So the Pythagorean identity and equivalent forms chart. This is a super important thing to know for the test and be able to do some examples with. If we have this, we can get some equivalent forms by dividing this out. So let's do it over here. Let's see how they got this. So when you're trying to write equivalent forms of sine squared plus cosine squared equals 1, always start with that. Like, this is the one that you can just remember off the top of your head. This is the one that, like, that's your base form. And then you can use things that you know about trigs and different trig identities and reciprocal functions to do that. So they get this one by, let's divide by cosine. Yes, let's divide by cosine. Like, they're getting this by dividing the whole thing by cosine squared x. So we're going to divide by cosine squared x, or theta, sorry, on this whole thing. Dividing by cosine squared theta the whole way across. This gives me sine over cosine is tan squared theta. Cosine over cosine is 1. Like, these cancel out when you divide them. And then if I divide, this will give me 1 over cosine squared theta. And 1 over cosine squared theta is secant squared theta. Okay, so that's how they get that one. And if we start at the same place and instead divide by sine squared x, or in this case, I guess I should say theta, sine squared theta, we can get the same thing. So sine squared plus cosine squared. I keep forgetting to write my thetas. Trying to go too quick. And then if I divide each term by sine squared theta, okay, these will cancel out to 1. Cosine over sine is cotangent, and there's 2 of them, so cotangent squared theta. And 1 over sine is cosecant. Okay, so that's how they got those. And that's like, why that's important is like, okay, I could have just memorized those. Well, come later down the road, maybe you're in calc or maybe in an AP test, you can only remember this one. Like, you can just memorize this one and derive these on your own. Like, just quickly, like, write this down, and if I need this one or this one, I can just divide by cosine squared theta and sine squared theta just to get those, instead of having to remember them, okay? And for now, I'm going to skip these. We'll come back to these later in class if needed. So we can skip these for now. And let's just go to example 3. So now we're using, this isn't one we're going to use the Pythagorean identity. Okay, so let's write this in terms of sine and cosine, and in the end we want just cosine. So we're going to rewrite f of x equals tan x on top is sine x over cosine x. And then the bottom cosecant is 1 over sine x. So we can keep change flip that. Keep change flipping this. It gives me sine squared x over cosine x. Now, you're like, how in the world could I get this in terms of in terms of cosine? Because what you might be tempted to do is say, okay, I've got 1 sine over cosine, so I could rewrite that as sine x tan x, but it asks it for cosine. Well, we know, like with this one right here, let's use the Pythagorean identity. Sine squared x plus cosine squared x equals 1. Well, if I want to isolate, like I want to plug in this into my equation, right? Well, let's isolate this really quick for sine squared. So let's minus cosine squared x on both sides. And that's going to give me sine squared x equals 1 minus cosine squared x. So using that Pythagorean identity, I've got this guy right here that I can plug in for sine squared. And that's something that's going to happen a lot. You're going to solve for, like for example, you could go back here to my identity. Maybe you need to solve for tan squared and plug it in. So that would be tan squared theta equals secant squared theta minus 1. You're going to use these identities and solve for one of them to plug them in. Because this allows me to rewrite this down here. So if I plug in for sine squared x, I can plug in 1 minus cosine squared x on top over cosine x. And there's not really any division that you need to do here. Because I've done my job, right? It says no other trig functions, and it's just cosine. Technically, you could split this apart and do 1 over cosine minus cosine squared over cosine, but no need for that. Now, here are 2 sets of identities, okay, that are super important to remember, okay? This one, you kind of just have to remember, okay? We can try to come up with some clever ways in class to remember these. Obviously, you'll have open note for the test, but on the AP test, like, you just need to know these like the back of your hand. You need to know these like the back of your hand. In this one, I'm going to link a YouTube video, the Sinbad. It's a video called Sinbad and Cassette, and it gives you a visual and like story way to remember these equations. Because honestly, like these are pretty complicated looking equations. Don't let the variable scare you. That's just alpha and beta. It could just be like you could just see x, y. Like that's just a fancy way to write it. But what it's saying here is the first identity is that sine of a alpha plus beta, so is sine alpha cosine beta plus. So the top goes with the top. So if I wanted to write both of these, let's just so I can show you. So the positive version would be sine of alpha plus beta equals sine alpha cosine beta, and use the top one with the top plus cosine alpha sine beta. Okay, and then here the minus goes with the minus. So sine alpha minus beta sine alpha cosine beta minus cosine alpha sine beta. So the one thing to remember is that sine is same. Like if I have a plus in the original, my expansion form is going to have a plus as well. Same thing with minus, minus, minus. But with cosine, it's flipped. So you can see if I have alpha plus beta, it's going to be minus. And if it's minus, I'm going to have plus. Okay. And then the different double angle identities, I'll just show you examples of how to use these and just commit both of these to memory here. So, which of the following is equivalent to the expression 2 sine theta, or my theta in this case is pi over 14, and cosine of pi over 14. So, right off the bat, I've got 2 sine cosine, 2 sine cosine. So I know I'm using the double angle formula for sine. So 2 sine pi over 14 cosine pi over 14 can be rewritten as sine of 2 times whatever theta is. So sine of 2 times pi over 14, which gives me sine of 2 pi over 14, which simplifies to sine of pi over 7. Sine of pi over 7. So now, we have example 5. This one does it in the reverse order. It pretty much tells us we're going to use the double angle. 2 times x means double angle. Like, we're going to double the angle. That's just why it's called the double angle formula. And looking at the answer choices, there's a lot of different ways to write this one down. So let's start by writing it in the first one. So let's just, and notice here, the weird thing is that I have a 4 right here, okay? So I'm going to take the 4 out and just multiply it at the end. So take the 4 out and multiply it at the end. So what do I mean? 4 cosine of 2x equals 4 times, I'm going to rewrite, I'm going to separate these and just do cosine of 2x in parentheses. So cosine squared, and then my theta here is just x minus sine squared x. Okay, is that an option? If I distribute the 4 here, doesn't look like an option to me. Answer D is close, but not quite the same. So let's do the second version of the double angle formula. So 4 times 1 minus 2 sine squared. Distribute 4 minus 8 sine squared x. Close, but not quite. So let's do the last one. So 4 2 cosine squared x. And distribute 8 cosine squared x minus 4. Boom. And one thing you could have done to start with is just look and see, like for example, there's not going to be a plus in here. Like that doesn't match any of the forms for the double angle formula of cosine, so that can't be an answer. 4 minus cosine squared wouldn't make a lot of sense unless you had a negative here, so you can probably cross that one out. And this is the same, like this answer choice is the same thing as the sine formula, this double angle formula for sine. So you could process of elimination that, but I wanted to show you both. And then here, I've got my sum and difference formulas. So notice it's in the pattern of this angle, so that's my alpha. This is my beta. And the way I know that is because it's repeated on the other side. It's always going to be repeated on the other side in some form or another. Because notice here, A, B, alpha, beta, alpha, beta, alpha, beta, alpha, beta. It's always going to be repeated. So that's how you know what your alpha and beta are. And then I look at the order. I've got cosine, cosine back to back. So that lets me know I'm working with the cosine identity here. Because here, this is working with sine, cosine, cosine, sine. On cosines, they're paired together. Sines are paired together. So, and it's the subtraction version. So on this, remember they do the opposite. So if this subtraction right here, then it has to go back to addition here. So that means, long story short, I'm going to rewrite that. Cosine of pi over 8 cosine pi over 16 minus sine pi over 8 sine pi over 16. It's going to be equivalent to cosine of, remember, because it's minus here, we're using addition here. So alpha plus beta, so cosine of, my alpha is the first one, pi over 8 plus pi over 16. And to simplify this, you can rewrite pi over 8 as 2 pi over 16. Just ignore the pi's and just treat these like ones, if that helps. Then pi over 16, so 3 pi over 16. So cosine of 3 pi over 16. And cosine of 3 pi over 16 is C. So the figure shows a circle centered at the origin with an angle measure theta in standard position. The coordinates of P are pi 5, 12. What is the value of 2 sine theta? 2 sine theta. So remember, let's write out what sine 2 theta means. Sine 2 theta is, if we go back to our chart, it is 2 times sine times cosine. 2 sine theta cosine theta. Okay, now let's plug in what we know. Sine of theta, so 2. My sine of theta is, remember, sine is y over r. And cosine is x over r. And it already gives me my x is here, my y is here, my radius is 13. So that gives me 2 times my y value is 12 over 13, and then x over 13, so 5 over 13. And I can multiply the top, together, so 2 times 12. That gives me 24 over 13 times 5 over 13. Then multiply across, which gives me 120 over 169. And then our last example, we have the figure show 2 circles centered at the origin with angle measures of alpha plus beta respectively. In center position, the terminal rate of angle alpha, which is right here, intersects at the point at point P, and terminal angle of beta intersects at point Q here. Okay. The coordinates of P are -5 and the square root of 11, and Q is 2 and the square root of 5. Okay, this ought to be interesting here. So if we go in here, we can rewrite cosine. It wants us to find cosine of 2 alpha. So when you're given these, what I would start with, let's go ahead and write what sine of alpha and beta are. So sine of alpha is y over r, y over r, r is 6, so square root of 11 over 6. And then cosine of alpha is -5 over r. Okay, same thing over here. Sine of beta is square root of 5 over 3. And cosine is x over r, so 2 over 3. Okay, so for alpha, really, it doesn't matter which one you use. I just use the path of least resistance because it doesn't tell me a specific way to find this. So I'm going to use, I'm probably just going to use, okay, well, which number is easier on this? Cosine looks a lot prettier than sine because that's got a square root. I don't really want to deal with that. So let's rewrite it with cosine. So the double angle formula with just cosine is 2 cosine squared theta minus 1. This one right here. So this equals cosine of 2 alpha, same thing as 2 cosine squared alpha minus 1. And let's plug in. Cosine squared alpha is, we already found that, is -5 over 6 squared minus 1. and that is going to 2 times 25 over 36 minus 1. And then that's going to multiply here, 50 over 36 minus 1. And then if I rewrite that as a fraction, I can subtract these. 1 is just 36 over 36, which will give me 14 over, don't know why my iPad's being weird, 14 over 36, which is the same thing as, sorry about that, 7 over 18, okay? And then sine of alpha plus beta, sadly, there's not a path of least resistance that we can really take here. Just got to write it out. So alpha plus beta is just going to be the sine formula, remember, starts with sine of alpha plus beta. I'll look back at my chart. Sine, the sine stays the same, so add is add, and then it just alternates. It starts with sine alpha, cosine beta, then cosine alpha, sine beta. It always starts with the alpha. Alpha starts. Alpha must start. Sine alpha, cosine beta plus cosine alpha, sine beta. Okay, so that's going to give me sine of alpha is square root of 11 over 6. Cosine of beta is negative 5 over 6. And then here. Oh, what did I make the mistake of? Cosine of beta, right? Because I use cosine of alpha, which is incorrect. Sorry about that. But that's why it's super important to, especially if there's so many steps, you got to make sure that you're using the right one. Cosine of beta is right here, 2 over 3, plus cosine of alpha is negative 5 over 6 times square root of 5 over 3. So I'll multiply those across. Sorry, my pen's going crazy. 2 square root of 11 over 18 minus, it's not a negative. My pen, it's just not want to work. See, it just drew a random line here. 5 times the square root of 5, oh, it was negative, sorry, minus or plus a negative, so this is plus a negative. So I'm just going to rewrite this as minus. That's why I had it as minus. Sorry, my pen got me really distracted. 5 square root of 5 over 18. Because these are already common denominators, you can just rewrite them. And that's as simple as you can get with that one. Okay, one more. So cosine of alpha minus beta. So cosine alpha minus beta is going to be the same thing as cosine alpha, cosine beta plus sine alpha, sine beta. And that's the same thing as cosine of alpha, we already found was negative 5 over 6. Cosine of beta is 2 over 3. And then sine of alpha is square root of 11 over 6. Okay. Multiply across, that gives me negative 10 over 18 plus, you can multiply, since these are both radicals, you can multiply the inside, so that gives me square root of 55 for 18, and I can add those together and get negative 10 plus the square root of 55 over